Optimal number of clusters. Determining the optimal number of clusters in a data set is a fundamental issue in partitioning clustering, such as k-means clustering. This requires the user to specify the number of clusters k to be generated. If you plot k against SSE, you will see that the error decreases as k increases. This is because their size decreases and hence distortion is also smaller. The basic idea behind partitioning methods such as k-means clustering is to define clusters such that the total within cluster sum of square, WSS, or the total intra-cluster variation is minimized. The elbow method looks at the total WSS as a function of the number of clusters. One should choose a number of clusters so that adding another cluster doesn't significantly improve the total WSS. It works in the following way. Compute clustering algorithm for different values of k, for instance by varying k from 1 to 20 clusters. Calculate the total within cluster sum of square WSS for each k value. According to the number of clusters k, plot the curve of WSS. The location of bend in the plot is generally considered as an indicator of the appropriate number of clusters. Cluster-based incentivization. Problem scenario. Lithium Power is the largest producer of electric vehicle e-vehicle batteries. They provide batteries on rent to e-vehicle drivers. Drivers rent a battery, typically for a day, and thereafter replacing it with a charged battery from the company. Lithium Power has a variable pricing model based on the driver's driving history. Battery life depends on factors such as overspeeding, distance driven per day, etc. You are supposed to create a cluster model where drivers can be grouped together based on the driving data and to group the data points so that drivers will be incentivized based on the cluster. Let's import the libraries NumPy and Pandas. Import visualization libraries, namely matplotlib and Seaborn. Import the warning module. The warning module was introduced in PEP 230 as a way to warn programmers about changes in language or library features in anticipation of backwards incompatible changes coming with Python 3.0. Import matplotlib library for visualization and an instance of RC params for handling default matplotlib values. Please note, for the sake of simplicity, we will take only two features: mean distance driven per day and the mean percentage of times a driver drove higher than 5 miles per hour over the speed limit. Let us go through each of the columns first and understand them. The ID column represents the unique ID of the driver. The mean _dist _day column represents the mean distance driven by driver per day, and the mean _over _speed _pers represents the mean percentage of the times a driver drove higher than 5 miles per hour over the speed limit. Let's start with using Pandas to read driverdata.csv as a data frame called df. We will now use the info command to check the number of columns in total and entries. Also, this will let us know if we have any missing values. In addition to it, we will use the describe function here to check the count, mean, and median values for each column. Now we will import k-means from sklearn.cluster and run the algorithm with k equals 2, which is the minimum number of clusters that can exist in a data set. Also, let us create an instance of the k-means model with 2 clusters such that it becomes easier to call the same later. Please note that we have dropped the ID column as it doesn't have any reference in forming clusters. Let's now fit the model to the data. The algorithm is now fitted on our data, and you can claim that it has created the clusters. Let us now use some commands to get some information on these clusters. We will use the command cluster centers from k-means to determine the cluster center vectors. Use the labels underscore command along with print to display the labels. Also, we can go for the length of those labels. Now let us check how many unique drivers are there in the first and second cluster. We will set the theme as white grid, as it is better suited to plots with heavy data elements. Plot the clusters using the lmplot function from the Seaborn library such that we have mean underscore dist underscore day feature on x-axis and mean underscore over underscore speed pers on y-axis. We can clearly see from the graph plotted that there are two clusters, one centered around 50 mean distance delay and the other around 175. Also, we can see that there are more drivers in the cluster with the delay centered at 175. Since k-means clustering gives optimum results when iterated multiple times, let's try out the same with increasing the number of clusters, say 4. Print the cluster centers with 4 clusters and track the 4 unique labels along with their frequency of occurrence. Zip the unique number of cluster and their frequency counts within a dictionary. We can clearly see the difference now in cluster centers. Also here we have a distribution of data points in each cluster. Let's now plot the same. Such that we have mean underscore dist underscore day feature on x-axis and mean underscore over underscore speed pers on the y-axis. From the 4-cluster plot, we can see that it's denser compared to the 2-cluster plot and hence more optimal. Now that we have clustered the data with the k-means, let's quickly recap the steps we have covered. Import libraries and the data set. Fit the k-means model on the data set. Evaluate cluster centers and labels. Plot the clusters to see the distribution of data points. Iterate the same by changing the number of clusters to 4. Again, evaluate the cluster centers. Plot the clusters to see the distribution of data points. Draw inference out of both